Today we're going to do trig functions, but even though the instructions say we're going to do 6, we're not. We're only going to do the 3, and the 3 we're going to do are sine, cosine, tangent. And often the order is remembered through what's called Sakatoa. So we're going to go through this. Here's our right triangle, So we're going to write our sine of theta, and theta is the symbol represented right here. So we're going to do sine is opposite over hypotenuse. So opposite over hypotenuse, our opposite is 8, and our hypotenuse is always across from the 90-degree angle, so that's over 17. So there's our ratio for sine. Cosine theta is adjacent. Adjacent means the line that runs with the angle. So 15 is adjacent, and it's also over the hypotenuse, 17. And then finally, tangent theta is opposite over adjacent. So opposite over adjacent is 8 over the 15. And so we have our trig functions according to tangent. So we're going to do that again with this triangle, and I'm going to go ahead and write Sakatoa just as a reference. So we're going to find sine of theta, and sine of theta is opposite over hypotenuse. The cosine of theta is adjacent, so adjacent over hypotenuse. And tangent is opposite, so tangent of that is 8 over 15. And so there's our answer. What we're going to do with this problem is we're going to find the sine, cosine, and tangent of angle B. The problem is if you're missing a side. So to find the side, we're going to refer back to an Algebra 1 concept of the Pythagorean theorem. So let's find that value first. So to find that value, we're going to have a squared, and B happens to be 5, which is squared, equals C, which is the hypotenuse, squared. So we get a squared plus 25 equals 64. And if I subtract 25 from both sides, 25, I'm going to get a squared equals 39. And if we take the square root of a, we end up with a being the square root of 39. So this value equals the square root of 39. Once we have that value, we can find sine of b, and in this case, sine of b is opposite over hypotenuse. So opposite is 5 over 8. So that one's already given to us. But then when we go to cosine b, that is the adjacent, and adjacent of b would be a, which we now figure out is square root of 39 over our hypotenuse. And then we have our final tangent of b, which is opposite over adjacent, so it would be 5 over radical 39. Now we're going to go back to way back when we did radicals. Radicals have to be simplified, and you can't have a radical in the denominator. So I'm going to multiply by that radical in the denominator, which removes it, because a pair comes out of the radical. And so we end up with this value. And we already have these values for sine, cosine, and tangent. In this example, we have to draw our triangle. So I'm going to draw our triangle. And tangent of B, and we know this is 90, tangent of B, and I'm going to label this B. The tangent of it is 3, that's opposite over adjacent. So what we don't know is this. So tangent of B is the opposite over adjacent. And now I need to find C in this case. So 3 squared plus 7 squared equals C squared. And this is 9 plus 49, which happens to be 58, equals C squared. And so to find C, I take the square root. So square root of 58 equals C. Now I have this value of square root of 58. So I can now go through and find sine of B. Sine of B is opposite, so it's 3 over radical 58. Once again, we have a radical in the denominator, so we have to multiply by it. Radical 58 multiplied gives us 3 radical 58 over 58. So there's my value of sine. So then we find cosine of b. Cosine is the adjacent 7 over radical 58. And once again, we have to rationalize the denominator. And we get 7 radical 58 over 58. And we already know what tangent is. So tangent of b equals 3/7. Now we're going to do some reviewing here. We've already used the Pythagorean theorem a couple times, but there's a rule with the Pythagorean theorem that we need to understand. That can we tell if we have a right triangle? And to do that, if 3 and 4 are squared, then you equal the value of 5. So I'm just going to run this test. 3 squared plus 4 squared is equal 5 squared. That's 9 plus 16 equals 25, and that's true. If this statement is true, then we have what's called a Pythagorean triple. So I'm going to test that with these two examples I have here. So let's go 7 squared plus 8 squared equaling 9 squared. Let's see if this is true or not. We have 49 plus 64 equals 81. Obviously this is not true. So this is not a Pythagorean triple. Now let's try the next one. 12 squared plus 35 squared equals 37 squared. Obviously this problem we're going to need a calculator for. So as I calculate, I know what 12 squared is. It's 144. So let's do 35 squared, and it's 1,225. And then all I have to do is do 37 squared, and it equals 1369. So if I add these two, do I get 1369? And I do. So this is, yes, a Pythagorean triple. Special triangles, the 30, 60, 90 triangle, this one right here, and the 45, 45, where the cosine and tangents and sines are relatively fixed. So we can find a missing side by substituting these values. So I want to be able to find this side, and I need to know which trig function to use. We have sine, cosine, and tangent, but what's given to us is an adjacent angle and the opposite. So the adjacent is the cosine function, but it's cosine of, now we know what the angle actually is, 30 degrees, and it's x over 8. Now, our special triangles, we know what the value of that is. So if we go up here to cosine 30, we get radical 3 over 2. And I'm getting that from right here. And that equals x over 8. And when we have all numbers and a letter, we can solve by just removing this 8. So I'm going to multiply both sides by 8. And when I do that, they cancel on this side. And 8 cancels with this 4 times. And so I end up with my answer is 4 radical 3. So that's what the value of x equals.